So anyway, in the middle of the slides, there's this problem right here. Oh, hold on, guys. My 5-year-old just went in to help with my 11-year-old in his online class. So I'll be right back. Hey, Finn, you need to sit down, right? Because James is doing class. Sorry. Okay. So so here's this problem that's on this slide, or on this PowerPoint slide. And I made a separate video where I went through my way of doing this problem and how I solved it. But it's kind of illustrative, because here what you know is a fixed position A, and you know a fixed position O, and you can kind of refer or kind of use that and anchor your analysis. So the distance of your piston cylinder is opposite this angle theta, and so you can relate the changes in the piston cylinder size to the angular size through trigonometry. And I did use law of sines and some right triangles, and I think in the book they use law of sines and law of cosines. So the algebra looks a little different, but the end result's the same. So that's kind of a typical kind of problem you might have here in these absolute motion problems. Okay, so the strategy is to write down, say, a distance as a function of some angle. And then if you want to find velocities and angular velocities, you just start taking a bunch of derivatives. That's right. Hopefully right now, I guess I'm the source and you're the observer, but when we do the group problem, it'll be the other way around. All right. Okay, so, and then in the slide, or in the video, I went through this example, so I won't do that one now. Other than to just point out that it's kind of the same thing. You have a fixed point A, and you can relate, and what they want you to do is to relate the horizontal velocity of this slide, this rod that slides, to the angular velocity, and you basically just use properties of trig to relate the horizontal position to the cosine of theta, and then take some derivatives. All right, so hopefully you've watched the video, and let's go through the concept quiz. So in this concept quiz, they say that there's something, okay, and there's a position S, and it's given as a function of some angle with this sort of complicated, this sort of function. Who cares what it means? And they want you to come up with a formula for the velocity. And you have to remember that these are all symbolic relationships, and so you should imagine that everything could be a function of time. Angles are functions of time, positions are functions of time. So go through and calculate the velocity. So take a second and do that. All right, so even if you're still working on it, raise your hand in the participants thing if you think you know how to find the velocity. Okay, pretty much a lot of people have it. All right, Sam, how do you find the velocity? What's this, just in words, what's the strategy?
Isn't it the derivative position?
Yeah, so you're going to take a time derivative on S. It's exactly that. There's no mystery here. But make sure you do the calculus correctly. So take a second, write it down, see what you get.
Chain rule.
There you go. Good man. All right, so Lenny's got the idea. So chain rule, that's the key word. All right, Lenny, no pressure, but here in a second, I'm going to have you tell us your answer.
I'll do my best.
Okay. Everyone turn off your video so you can laugh at him and he won't know.
Yeah, do it. Not the bunch of laughing.
Okay, so Lenny, what do you get when you take that derivative?
So there's one thing I'm not sure about, but I think it's C.
I think it's C. Well, just you think
Oh yeah. Wait, no.
No, it's A.
it's A. Okay, so let's go through that.
That makes sense because omega equals d theta dt.
Yeah. All right, so let's go through that on the other screen here. Oh dear, I didn't get my iPad turned on.
Maybe if you had a Microsoft tablet, it'd work better.
Yeah, well, it also would work better if my kids hadn't dropped it multiple times, and it's like I'm a little afraid I'm going to get cuts here on the jagged edges. Oh dear. Okay, so what we have is that S equals 10 sine of 2 theta. And you have to remember, theta and S are both functions of time. You should just assume. So when I work out S dot, that's going to be, so I take the derivative on the outermost function, and then you work your way to the innermost function. So the outermost function is just going to be 10 sine of whatever. So the derivative of that's going to be 10 cosine of 2 theta. And then I have to take the derivative on the innermost function, which is going to give me a 2 times theta dot. So the answer is going to be 20, and theta dot is omega, and then I have cosine of 2 theta. Okay, so I get answer C as my answer there. Is that okay? Raise your hand if that makes sense to you. Okay, so Muhammad, when you were doing that, what you said was A. That's what you would get if you took the derivative with respect to theta, but we're not. We're taking the derivative with respect to time, and so you get that extra chain rule factor. Okay, so let me switch back here to PowerPoint. Okay. Oh, shoot. Can everybody see the PowerPoint? All right.
Yes.
Okay. I'm still juggling. I just have my laptop here, so my connector to the other monitor is supposed to come tomorrow, so then I can space things out and see everything all at once. All right, so then go through the same process and find the acceleration. So take a second, do the calculus, find the acceleration. You guys can put your hand down. You're going to block somebody's view from the back of the room. Kirkland. Nick sits in the back, so it doesn't matter about him. Oh, so now we see that Kirkland's not even there. She's probably out in the kitchen getting breakfast. I see. All right, so go through same process and find the acceleration. So to find the acceleration.
So wouldn't it just be a product rule?
Yeah, well, it's a chain rule and a product rule. You kind of
Yeah.
have everything. Yeah, that's right. So you see, when you start working out higher derivatives, if everything is actually secretly a function of time, it gets big. Just the expressions get big and clunky. We'll see that in the group problem here in a minute. So if I switch over to my iPad, then what we found before was that the velocity, I don't worry about that. The velocity was 20 times omega times the cosine of 2 theta. And theta is a function of time, but omega is also a function of time. Okay, so I have to remember that. So the acceleration is going to be 20 omega dot, that's alpha, times cosine of 2 theta. And that's the derivative on the first part. Now I have to have the derivative hit the second part. Because remember, when you have the product rule, it's like, I always think about the derivatives like you're sprinkling them in and everybody gets it a little bit. So now I have to take the derivative of the cosine term, or cosine factor. So I get minus, and I have a 20 omega, and I'm going to get sine of 2 theta. But I had to do the chain rule on the argument of sine. So I'm going to have to multiply by 2 omega. I'll put it, multiply by that. So when I pull it all together, I get the acceleration equals 20 alpha cosine of 2 theta minus 40 omega squared sine 2 theta. The sign is right on the crack in the screen. All right, so now let me switch back to the PowerPoint presentation and see what my options are. And and sure enough, that's option B. Okay, so you see how, because you have to keep, because everything is an implicit function of time, when you take these higher derivatives, you typically don't just get a nice simple little thing. They get bigger and bigger and bigger. If I ask you to find the jerk,
Point at Sam.
I'm waiting for Sam to throw something in there. If you had to find the jerk, you would take a third derivative, and you're going to have a product rule and a chain rule on this bit, and then you're going to have a product rule and a chain rule on this bit, and they just keep growing and growing and growing. Okay. All right. Are there questions on that? Raise your hand if you want me to go through that in any more detail. Okay, good. All right. Okay, so I want you guys to. Okay, yeah.
Wait, Sean, if you could repeat that part, I just got in here. That last part you just said about a jerk and Sam.
Well, I can't say it now that you're here.
Oh.
So the jerk is just the third derivative of position, and so I was just saying that you would have to. So the answer was option B, but you have to remember, even though people don't write it out, alpha is a function of time, and theta is a function of time, and omega is a function of time. And because everything's a function of time, at some point you just assume everything's a function of time, and you don't bother to write it down anymore, because otherwise the equations just take forever. But that means when you do the calculus, you have to be careful and really follow the rules using the chain rule and product rule and all that stuff. That was really the point. Okay, so great. So what I want you guys to do, let's see, it is 10:22. So what we're going to do is we're going to take 10 minutes. I want you guys to I'm going to give you guys 10 minutes to talk to the people who are normally at your table. Arnaldo, you can ask me questions if you have them. I won't answer them, but that's okay. I'm going to give you the group problem here, and I want you to chat back and forth with your partner and try to talk your way through doing it. Tim, do you know if they can use the whiteboard space? I'm not sure if they can between each other. Do you know?
No, I think it'd be shared with everybody.
Okay. Well, I tell you what we'll do. I want you guys to talk between each other, and then maybe I don't know, maybe we'll do this whiteboard thing, or maybe I'll do it here on my whiteboard. I have a physical whiteboard behind me too, so I can do that as well. All right, so here's the problem. It's lots more fun than the ones we've seen. Maybe. There we go. Okay, doesn't that look nice? Yes. Okay, so what you have here is a cam, a circular cam. It rotates. It does not rotate about the center. It rotates about point O. So the axis of rotation is off center. So if you think about what that will do, it makes the green circle wobble. Okay, can you imagine that? Raise your hand if you can kind of see how that would work. One.
Wait, repeat that, Sean.
Yeah, it's the green circle is going to rotate, but it doesn't rotate about the center. It rotates about point O, which is going to mean that it kind of wobbles, right? So,
Okay.
right? And so what that's going to do is the smaller wheel, A, is going to stay in contact. So you can imagine there's a spring somewhere holding it in contact. So what that's going to do is cause the roller A, or actually the rod AB, to kind of slide back and forth in an oscillatory kind of, fashion. Okay, so because of the wobble in the cam, it makes the rod go back and forth, and kind of have some sort of complicated motion. All right, so hopefully that makes sense. So they say you're allowed to use the following symbols, basically. The radius of the displacement of the axis of rotation from the center of the green wheel is a D. The radius of the green wheel is R, capital R. The radius of the small wheel is little r. And you have an angle theta right here. And they tell us that it is rotating counterclockwise. So that means that omega is positive. So I would measure everything with respect to the standard math conventions if I were you. I mean, I find that easier for me so that I don't overcook the minus signs. And then what the goal is to find a formula, and it'll be a symbolic formula for the velocity of the rod AB as a function of the angle. Okay, so this is going to be a symbolic problem. You're going to have chain rule, you're going to have trigonometry, you're going to have all kinds of fun. I'm so excited for you guys, really. Okay, so the plan, all right, so here's the plan. Set the coordinate x, so that's x is the position of the little wheel here, to be the distance from the pivot, the axis to the center, or to A. X is going to be the distance from O to A. I don't know why they made the red line go all the way that way. Anyways, that's what they did. And then you're going to come up with a triangle to relate this distance to the angle theta. So you come up with, that's my hint. They don't use the word triangle, but that's my little gift to you, I guess, is come up with a triangle. It won't be a right triangle. Okay, so come up with a triangle, and then once you get that triangle, then you're pretty much home free, and you just start taking derivatives of everything to relate omega to velocity. Okay, so break out with your partner, and Arnaldo, if you want to, you can do a private chat with me, or I don't care, whatever. If you have a question to ask. So I'm going to give you 10 minutes to kind of talk to your partner, and I will just start up a private chat with Tim, and we'll just make fun of you guys. So, seems fair. If you guys got stuck, raise your hand and I'll try to help out. Okay, Thomas raised his hand. So now let me, oh, do you still need help, Thomas? Yeah, okay. So let me
Yeah, I'm kind of lost right now.
well, so what you need to do, all right. Let's see if I can join the chat. I don't know if I can. I don't think I can. All right. So what you need to do is come up with some sort of an expression relating x, right? Because that would be the distance from the axis of rotation to where this rod is. So if you know x, you can take the derivative to find the velocity of the rod, because it's just going to be the same. And my suggestion is to come up with a triangle. I'll even suggestively trace a triangle out on the screen. Right? So come up with a triangle and then use that triangle, maybe properties that you know about triangles, to relate the angle theta to x.
Oh, I see it now. Okay.
Is this like a law of sine kind of thing, or?
I think that would be a good thing to know.
Well,
You
I
don't-
don't know.
You don't know it. I talked to your statics person there. So you guys all remember law of sines? So the law of sines says when you have a triangle, then the ratio of the side opposite angle divided by the sine of the angle is the same for all three. So it's the opposite side divided by the sine of the angle for all three angles. All those ratios are the same. That's going to be a useful thing. At least that's how I did it. Just so I know, can you raise your hand if you guys are having constructive conversations? Two.
I just started copying the.
Oh, okay.
problem.
All right. That's fine. That's
Don't
fine.
worry. Don't worry.
All right. Good. You know, this coronavirus thing keeps going. I mean, I realized I could start drinking. I can start teaching with a bottle in my hand. So, you know, might not be so bad.
Yeah. Right.
Way ahead of you.
JCC is substance free, but my kitchen, on the other hand,
Governor did declare that alcohol stores are essential, right?
yeah. I'm doing it for the greater good.
Self-sacrifice is what it's all about.
Yeah. Um,
I don't know.
Is anybody stuck? Thomas is, okay. What's up, Thomas? And Shane is, okay. What's up?
I'm just so once you do like the law of science,
Yes.
and you get your oh wait 1 second. There's a bunch of background noise.
So yeah, like one of my questions is when you do you for this one, would you have to introduce like a new angle and keep it arbitrary?
So that's what I did. I like to do that. The book used law of cosines, which allowed them, I think on this problem, we'll look on the next slide. If I remember right, when they did it, they used law of cosines, which allowed them to not do that. But that's what I did.
I'm starting with law of cosines, but it's getting complicated.
Oh, the formula is going to be gross. So it's not like it's going to be a, okay, buddy, but I'm still teaching. Great job reading. Can you go find another book? Because remember Southwestern, what do we got? Or Trojan Readings, you gotta go for an hour. So can you do?
They don't always go for it.
I know, but here at
JCC.
here at the Nowling School, we're going an hour because that's how long my class is. So so tell you what, go get Calvin and Hobbes. Go read Calvin and Hobbes. That'll be good. Yeah. Calvin.
Why don't you read then why don't you read your physics books?
I would.
Erase.
Hey.
There you go. Help him out, buddy. He needs it.
Hey buddy, do you know how to do the law of cosines? We need some help.
Question mark, question mark, question mark.
Yeah, I feel you, bud.
Was that a
I need for you to go to the other
question?
room. Go get your Calvin and Hobbes.
Exclamation mark.
Oh boy, here you go, bud.
Scream.
I knew Sean never read those books.
9.
There you go. The days are just packed. Come on. Okay. Come on, buddy. They're supposed to be working really hard on a problem, and if you show them how much fun you're having, they won't get their work done. So that'll be bad. So why don't you?
I love all those things.
He told me the other day he wished coronavirus would go on forever. I don't think he's missing school much. All right. How are we doing? It's been a few minutes. Are there groups that are stuck?
I'm just having a little trouble with the calculus for law of cosines, but
Okay. All right, well, we'll work through it.
I think I'm doing it right.
Okay. Nobody's saying they're stuck, really. Okay, so I'll give you guys, say 3 more minutes, and then I'll start going through it.
Yeah, like I understand the triangle part, but I'm just like trying to figure out. I've been trying to attack at law of cosines and sines, and it just gets to some points where I'm just unsure of what my next like decision.
Okay. All right, so then let me step in, and I will go through this. Okay. So I'm going to switch over to the webcam and the screen or the whiteboard behind me, and work it on the board. Okay. Okay. So should have made sure I'm set up. Let's start this. All right. Okay. So I did not use law of cosines. I just didn't think to. That might be an easier way to do it. So I have a large wheel, Oh, I should ask, can everyone see that? Is that okay?
Yes.
Yeah.
All right, I have a large wheel. The center of the wheel here is going to be right there. The radius of the wheel is R. And then there's another wheel, which is smaller. And it has a radius lowercase r. And then the axis of rotation is here. And this is a distance d. And I've kind of got things a little bit on a diagonal. So, okay, so it's like this, and this is point A, and then I don't know, point B or something like that. This is the rod that's going back and forth. Okay, so this is I want the velocity of this segment. And this angle is called theta. Now, one of the things to notice about this, which will simplify the calculus, is that d is constant in length. And notice the wheels are incompressible. They're not made of rubber. So that means that this side of the triangle also has a constant length. So as these things rotate, the line between the two centers of the two circles is going to be a constant, big R plus little r. It'll never change. That's kind of a nice fact. And, okay, so let me kind of stop there. Is that clear to everyone that this is never going to change?
Yeah.
Yeah. So, okay. So, Lenny, you have a question, or let's see. Raise your hand if it's clear. Maybe that's the way to say it. Raise your hand if it's clear. Yeah. Okay. So that's going to help the calculus part of it. And then what I did, I'm going to clean up this, just give myself a little bit of room.
So Sean, basically like the thought process of this is like that theta is going to be changing and like that what they called like X on the picture.
Yes, that's right. And those are the only two things that change.
Okay.
And when I did it, I went ahead and defined a new angle phi, just because it helped me kind of identify a block or a thing that I could manipulate, algebraically. But I don't think, if I remember right, they did not do that. It's okay, because in the end, I'm going to introduce it, and then I'm going to algebraically remove it from the problem. Okay, is that? Alex, you have a question?
No, I just had the hand raised for the
Oh, okay. All right. So, first thing I did was law of sines, and that told me. So for theta, what is opposite theta? Well, opposite theta is big R plus little r. So I had that sine of theta divided by big R plus little r. That must equal sine of phi divided by d.
Wait, Sean, why did you say that you put phi in that corner of the triangle? Because you already knew d. Is that because it's constant? Is that what you did?
Well, I knew I was going to use law of sines.
Yeah.
And so I just needed to give it a name.
Okay, so you just okay.
Yeah. But
I didn't know, like, since you know that is it because x is like varying? Is that why you didn't put x down right there?
oh, I'm going to come up with an equation for x here in a minute. So I'm not done.
Okay.
Yeah.
Okay.
Just give me a second. And then, okay, so I have that, which allows me to, I'm going to multiply both sides by d. And that's going to give me kind of my dictionary relating theta and phi. So I introduced phi just as a kind of, for me, it was really more of a mental placeholder. So algebraically, I could kind of move things around. But ultimately, this is how I'm going to get rid of phi and replace it with a theta when it's all done. All right. Okay. The other thing I have is I'm going to draw a perpendicular down and break this irregular triangle. What do we call those? Scalene. Is that right? Anyways, this irregular triangle, I'm going to break it into two right triangles, and I can use, because it's a right triangle, I know that this distance and this distance can be related to cosine of theta and cosine of phi. So after breaking this triangle into the two smaller right triangles, I can say that x equals d cosine theta plus quantity r plus little r cosine of phi. Let me stop there. Raise your hand if you understand this.
Can you go through that logic again? So you're saying that x is like the full distance.
X is the
like,
distance
B
from
to A?
O. I should have labeled it here. O is
O to
right
A.
here at this vertex, and A is there. So X is from O to A.
Yep.
And then I'm breaking this irregular triangle up into two right triangles so that I can do normal trig.
Oh, I see. That makes sense.
Mohammed, you had a question.
Yeah, I just wanted you to repeat how did you solve for the x?
Okay, is that okay? But the X is this whole length here. And I broke it into two pieces which are connected to right triangles.
Okay, right.
When you do these problems, you'll find there's a finite list of tricks. This is
Yeah.
one of the tricks. And so if you see it, I think the next time around it'll be kind of clear.
Alright, I got it.
Okay. Right. So, all right, at some level, I'm done. I just have to solve for theta in terms of in x. It's kind of complicated though, because I've got all these trig functions and I've got this angle phi that I have to get rid of algebraically. So the thing to remember, think about this wheel. As it goes around, the cam, it'll never get hooked on the back side of the small wheel, right? Because otherwise the whole thing's broken and it'll just snap the rod. So what that really means is phi can never get larger than 90 degrees. Because if it does, the cam is going to hook onto the wheel and break the whole thing, the rod.
Is that type of thought process common in like all these type of problems? Because that was like the same thing you introduced in the window example that was kind of confusing.
I think I will ask Tim to step in here. That's how I picture it and kind of thought about it.
'Cause for the window example, this is the part where I just kind of lost in it.
So personally, because I find the formulas, they get so complicated, I can't just look at it and say, oh, that's right. So it's
that makes sense.
For me, I like to pick a couple. I like to kind of know what is the maximum and minimum values of things. Like how big can the angle be possibly? And then that kind of helps me plug in and check that I got something right. You know, like in the window example, by plugging in, I knew that, okay, the biggest angle was 180 and the smallest angle would be 0. And then what X values did that correspond to? Or what S values did that correspond to?
Okay.
That's how I do this. I don't know. Tim, I don't know. Do you have any other thoughts there?
It makes sense to me. I mean, you're looking at limiting values to try to test, whether what the bounds of a variable are, right?
Yeah. And the other thing is you kind of have to know yourself. And for me, I know where am I going to get this wrong? It's usually, I don't get it wrong on the setup. Usually I'm pretty okay on that. For me, I get it wrong in the arithmetic. And so by having some values I could plug in or think about, that helps me.
I'm in class.
What's that?
Oh, my bad. My fun.
Hey, bring him back. Now you have a partner. Okay. Okay. So for me, because I know that I know that phi can never be bigger than 90 degrees, or else the whole thing is broken. That means that cosine of phi is never going to be negative. It's going to be a positive quantity. So now I can go back and I know that cosine squared phi plus sine squared phi equals 1. But because cosine of phi is always positive, I can write cosine of phi is equal to the square root of 1 minus sine squared phi. If you didn't have that, if it switched signs, you might have to worry about do you need to take the negative square root? I have a suspicion that actually, if you kind of close your eyes, that in the end, when you work it out, it doesn't matter. But you want to check that.
Wait, Sean, we're solving for the function of position. For some reason, I thought we were solving for the function of velocity.
Well, okay. The way these absolute motion problems go is right now we're doing geometry, and we're solving for x. We want x as a function of theta. That's what we want. And then after we get that, like in the little quiz problems, after we get that, we take one giant derivative with respect to time to work everything else out.
Well, if we just took the derivative as it stands right now, and we had like that, the term on the right turns into negative sine theta r plus r. Like, can't we just plug that sine of theta?
Oh,
sine of phi. Sorry, can't we just plug that equation that we have for sine of phi into that one?
that would work, Thomas. I didn't think of it that way. That would work. So you see what Thomas is recognizing? That when I take a derivative, I'm going to get a sine, and I could just straight ahead do that. That would work. It would work.
And then you just, the r plus r's would just cancel out. And
let me give me one more time to think. That would work. As long as you did not need to know x, if all you wanted was the velocity, that would be okay. But if you wanted to find x, you're still going to need to do the next step. So it depends on the way the problem's worded. So yeah, so good. I just kind of dove into the algebra. I didn't think about that fact. Anyways, so let me continue this line of reasoning, since that's the kind of path I'm on. What I can do is relate cosine of phi here to sine of phi, but I can relate sine of phi to theta. So when I go through that, I can say that this is going to be d cosine of theta plus, and I have r plus little r times the square root of 1 plus sine square of theta, or sine square of phi, but that's related to the square of this. So I'm going to get d squared over big R plus little r, quantity squared, sine squared theta. So I related cosine of phi to sine of phi, and then sine of phi to sine of theta, but the price I pay is all this crap. And then I get d cosine theta plus, now I distribute this to the inside, and this becomes the square root of r plus r squared plus d squared sine squared theta. Ugh. Sine squared of theta, not sine of 2 theta. I apologize. Alexa, stop. All right. It's kind of nasty. Raise your hand if you follow my logic there. Alexa, stop. Okay.
There was 3 times.
Now you can have a break. Go have a break time. Okay. Raise your hand. Yeah, Nick understands. Yeah, Arnoldo. Lenny, does that make sense? Are you okay with it?
Yeah, that makes sense.
All right. It's kind of gross. And Thomas, your method would avoid this. Well, it's not going to look nice when you're done either, but you wouldn't have it wouldn't have this reason.
Can you tell me what anything what of my options would be?
You can do, if James is done with his class, you can do TV upstairs.
Anything can I do something?
I could do that. No, I tell you what, you could do this if you want.
Videos?
Yeah, that's fine. But go to your room so it's quiet. All right. Okay, so I have that, and let me check. I make sure I didn't screw that up. No, I'm good. All right. Now I need to take a derivative to get a velocity. So I take a derivative of x. So the velocity is just going to be, I have a whole bunch of chain rule and all that kind of fun to have. So that's going to give me minus d times omega over, times sine of theta. And then the derivative of this is going to give me plus, and I'm going to have 2 omega sine theta cosine theta, and there's a d, divided by the square root of big R plus little r squared plus d squared sine squared theta. Write that a little better. So when I take the square derivative of the square root, it ends up downstairs. Oh, and I forgot my half. Like that. So I get a half from the square root derivative, power law. And then I get the square root. Now it becomes to the negative half power, so it all pops, shows up downstairs. And then I have to take the derivative of the inside. Well, that's not going to be right. That's going to be a d squared. Sorry, trying to do too much in my head here. It's going to be a d squared, and I get a 2 sine theta. Chain rule gives me a cosine theta times theta dot, which gives me an omega. Whew. Okay, raise your hand if you get something equivalent to that.
So Sean, why when you would do it if you did it the way that I said, why don't you get an equivalent
Oh,
answer?
It has to be equivalent.
Or it just looks a lot. There's a lot of simplifying you can do here.
I don't know. It should end up being about this gross.
I did it with log cosines and I got something different. And I didn't even
And
have a factor of r plus big R plus r in it at all. When you took the derivative, it just completely went away when you did log cosines. So,
well, so I haven't done it that way. So ultimately, the answer has to be. So what the answer I get is the same as what they are going to have in the book. So or in the slide. So I think this is right. I will after we finish. Let me sit down and write it out, and maybe I can do that. Okay. So this is how I did it, and it matches what they have. So I think this is going to be the right answer. But it must be that when you do it through some other method, it has to come out to be the same. It may, at least up to some rewriting of things. Okay, so what they do in the book or in the notes or in the slide is they regroup this, and they regroup and they use the fact that 2 sine theta cosine theta is equal to sine of 2 theta. So some of this numerator cleans up just a tiny bit, and they write it out as the velocity equals minus d times omega times sine of theta. And then I get plus, and I'm going to have omega, so I'm going to have plus d squared omega over 2 times sine of 2 theta divided by the square root of all that crap.
Wait, Sean, when you did the, I just realized something. Wait, so when you took the derivative,
Yes.
what did your, of the very first term, when you got negative d omega sine theta, when you took the derivative, how did you get the omega in there?
Because theta is a function of time, so you have a chain rule which gives you theta dot.
Oh, okay. Okay.
It's like the problem we did in the quiz. The whatever the, I don't know what they call it, whatever little quiz problem. Yep. All right, so let's see what they've got. Share. So that's what they have. Yeah, that's the same thing. So now they didn't use, so they never used, I don't see that they introduced this angle phi. So I think what they must have done, I don't know. I didn't work it through the way they did it. So I'll have to think about that. I will try to use the law of cosines and see what I get. And if I have time, I'll try to write it up. If not, maybe I can show you guys next class. Okay. All right. So raise your hand if you feel like you followed, at least you followed the way I did it. Raise your hand. All right. These symbolic ones, they get pretty gross in terms of just the formulas are not, when you deal with real world problems in general, there is no magic. It doesn't really simplify. It is as gross as you think it's going to be.
Yeah, like I kind of followed each step you did going along, but kind of just looking back at everything we did, I just think it's pretty overwhelming in a way.
It is. But what I will tell you, you guys are, maybe you saw me do an example. The window example I did was kind of similar to this, not quite as gross, but kind of similar. I think what you'll find is at the front end, it seems like, well, how would I ever come up with that? But what you'll find is there's only a finite number of little tricks. So it's not actually as wide open as you might think. So let's kind of recap how we did this. We were looking for, we really want x as a function of theta. Okay, so you're going to start, and you're going to use trig to do that kind of a thing pretty much every time. So you're going to come up with some sort of trig relationship relating x to angles. And then the problem is, for some problems, if everything's at a right triangle, well, then it's super easy. But where it gets complicated is when it's not a right triangle, and then you're going to have to do some sort of process to rewrite things so that you can kind of get it down to just one angle that's involved. And I think inevitably it's going to be equivalent to what we just did. You're going to take your irregular triangle and break it up into right triangles, and then just use sines and cosines to work your way around it. So even though it looks overwhelming, I totally, if you hand that formula to me, I just say, I don't want to think about that. It's manageable because it ends up being the same trick over and over. Let's see, maybe we can take some limiting values. Let's think about this. I'm just trying to think here. Let's see what happens. If you were to so if you think about it, as the cam rotates, when would you expect the turning points to be? I would expect the turning points to be when theta is at 0 or 180? Because at 0 and 180, that's when it's at the maximum and minimum eccentricity, I don't know what to call it, off-centeredness. Okay, so I would expect if I were to plug in 0 or 180 that the velocity is 0. So that would be a check we could do. So let's plug in theta equals 0. And when theta is 0, both those terms are 0 because they're both come out with a sign of 0. So that means the velocity is 0. The other check I could do would be to say when theta is 180, that's when you're at the, when the slider is as far to the, or the bar is as far to the left as possible. And so if I plug in 180 degrees, what happens there? So sine of 180 is 0. And sine, oh, and then sine of 2 times 180 is 360. It's also 0. So it's 0 in both cases. So that's at least some sort of a check that the velocity is 0 at both 0 degrees and 180. Is there another way to check this? Can we think of another way? I'm trying to think. Let's see, what else could I do? I think that's the only thing that comes up. I mean, the other thing you could think about would be taking another derivative, because you could say something about when the acceleration should change signs. But that's another, I mean, that's going to be even more fun, right? If the next problem was to find the acceleration, there's no magic. It's going to be as much fun as it looks like it's going to be. You have to keep track of the chain rule and all the little factors. Okay. All right. Do you want me, I don't know what else I can say about this example at this point. Let's go on and to the quiz. All right. Okay. So here we have our attention quiz. Okay. So actually, so I was up, I worked on this morning trying to run through the numbers because I was up late last night. I was tired. And I actually got something different for question 2. So I'll be interested. Maybe I screwed it up, but let's see. Let's go through the first one. So you have these 2 sliders. What's the first thing that you notice about that situation? Think about how these objects, these points A and B, are allowed to move. A is only allowed to move sideways, and B is only allowed to move vertically. So that's the first thing that kind of jumps out at me. And then as point A slides to the right, B is going to be pulled downwards. So that means that angle is going to be flattening with time. Okay. So if that angle flattens, so I'm going to define my angles. I'm going to say positive theta is kind of the counterclockwise theta. And so I'm going to be saying that in time, I'm expecting omega to be positive, okay? Because I'm expecting the angle, I'm expecting basically that bar to rotate in a counterclockwise fashion. So the change in angle should be a positive change. That's how I'm going to think of it. All right. So take a second and let's think about how you would do this. How could you come up with a relationship between the position at A and the angle? Take a second, See if you can do that. So you should be looking for a relationship saying like x equals some function of theta. Raise your hand if you think you have an idea for how to do that. Try the position. Okay, 1, 2, 3. Sam's got it. Okay. Alex. Okay, so Alex, how did you come up with a formula for the position of A as a function of theta? What did you do?
I mean, I thought of it like the Cartesian vectors, and then like took the derivative kind of thing.
That's it. Hey, there's no. Yep, that's it. This one's not nearly as complicated as the other one. So I'm gonna here. I'll do this on the board. I switch over to the webcam. So we have this wall and we have these points A and B. There's a rod between them and an angle theta. And so as this point moves over, I'm going to think about this distance. I'm going to call it x. And I would say that x equals, and I know the length of this. It was 2 meters. So I know that x is going to be 2 cosine of theta. Okay. Now, here's the thing. Yeah. Okay, that's fine. So here's kind of the way I thought about it, though, to get my minus signs right. If I have my x-axis here, if theta is going up from the negative x-axis, or sorry, up like that, then I'm going to actually say, when they say 30 degrees, I'm actually going to say theta equals minus 30 degrees, because as I've drawn it here, that's a clockwise angle. So that's actually a negative rotation. Okay, so I'm going to say that theta is negative 30. So there are always these issues. In high school trig, you just always say angles are positive. But now that we're talking about rates of change, the minus signs kind of matter. So you have to just pick something and live with that choice. So I'm going to say, because I drew this like that, going up, that's actually a clockwise. I had to move the marker clockwise, so that corresponds to a negative theta. Okay. But I'm expecting omega for the angular velocity to be positive, because I just physically see that it's falling down. So to get the minus sign omega correct, you need to choose that angle correctly. Okay, so that's my formula for this. And then I work out x dot to get the velocity, and that's going to be minus 2 sine theta times omega. Therefore, omega equals x dot divided by negative 2 sine theta. And the problem tells me that x dot is 10, I think. Yes. And what is sine of negative 30? Well, sine is an odd function, so that's equal to minus sine of 30, which is
negative square root of 3, right?
Hmm? Let's type.
Negative 1/2.
What's that?
Yeah, it's I was just saying it's negative 1/2 or 1/2.
1/2, yeah. So the half sine is going to give you a half, which cancels the 2. And because I have a minus sign in my angle, I actually get a double negative. and you get 10 radians per second. Okay, and it'll be positive. So that's positive in the so that means it's going to be a counterclockwise rotation. So you want this option. I think that's option A. I can't remember. I'll go back to the screen. So I think that's option A. Right? When I work out the next derivative, I get the following formula for acceleration. And what I get is minus 2 cosine theta times omega squared minus 2 sine theta times alpha. Sorry, it should be this should be sine theta. That's right. That's what I get for the acceleration.
Sean, we can't see.
Oh, sorry.
It's okay.
So that's what so for the acceleration, I take another derivative and I get minus 2 cosine theta, and then I get omega squared because I get 2 factors of omega there. And then I have to do, then I get minus 2 sine theta, and I have the derivative of omega, which gives me alpha. And then when you solve for alpha, now when I plugged in numbers, so I say that omega equals 10, and I plug in, they say the acceleration is 10. When I plugged in numbers, I got alpha equals negative 183 radians per second squared. And that's what I got when I plugged everything in, saying that omega was 10 and A was 10 and theta was 30, actually negative 30. When I look at the options they give me, they don't give me that option. The option they gave me was negative 173. So I don't know. Yeah.
I have a question. If we're like plugging in degrees, how are we getting radians? Like
Well, really what you could do, so the only place that you're actually converting is inside the trig function. So what you should really imagine is that the trig functions are actually always supposed to be in radians. There really is, you're never supposed to really use degrees. And so when you plug in, you can imagine that you're just switching it when you plug it in, is how you should think of it.
Okay.
Yeah. So when I did this, I got negative 183, and I did it twice. I kept getting the same answer.
I just got negative 183.
So I think they've got a typo and in the slide.
Because it's negative 173, but then you have to add that plus 10 from the.
Oh, is that what it's
double that?
Okay, so that's probably what happened. And I tweaked all the other little substitutions I could think of, changed sine to cosine to see, and I couldn't reproduce any of the other 3 options. So those are just random numbers. They're not. I don't think there's a simple way to get any of those other options. So I think the answer is 183. Okay, so I have to go. I have to get my kid on his own class. So I will think about using law of cosines and see if I can get that to work on the other problem. And I'll let you know. Okay, so I posted.
On YouTube, there is only one video. That's right? Because on your channel, I can only see one video, and I think you said videos. So I was just wondering.
No, I've uploaded lots of them. They should all be visible.
Oh, I only can see one.
Are you going through the link that he sent? Because he did send in like the first video separate, but now there's like a link that has everything.
Go through the Blackboard page, I think, and you follow that link.
I think that's what I did. I went to the dynamics and then went to YouTube, and it took me to like I think Tim's page.
Oh wait, you posted more videos than dynamics?
Yeah, that's what I was wondering. You know.
Let me.
Yeah,
I will add another link,
has
but
all
I know that if
dynamic.
you go to my YouTube page, if you go to my playlist or the
Oh, like for physics?
yeah, and then go to playlists,
Because
You
I got confused. I went to Tim's.
you can see all. Okay, no, it'd be under mine. So go to the physics one, and you should be able to see all my classes.
Okay, that makes more sense now. Because
Yeah. All right. So then you'll see that. So there's homework due on Friday. There's homework due next Wednesday, and there should be a video for the next lecture. I think I've already got that up. I can't remember if I uploaded it last night or not, but it should be there.
Yeah, you uploaded 16.5.
Yeah. So that's already up there. And I want to do next class kind of more like this, where you guys are solving problems. So please watch the videos. I'm going to assume that you've watched them.
so Sean, I'm in your like JCC physics page,
Yeah,
and
go to playlists.
there's 2710 physics, 27. There's two of them, 2710, and there's 1610. These are the playlists that I can see here.
Mohammed, can you share your screen with me through Zoom?
How do I share my screen?
I think you go to share screen at the bottom.
Hold on, I'll try to do that.
All right, I'm going to stop the recording though. Here.
Okay.